Our next goal is to classify points which were found using what we call the Fermat theorem, points which we called critical points, points which are suspected of being either minima or maxima, but are not necessarily. So let me remind you what we know. So if x0, y0 is a local minimum or maximum of fxy, and we're assuming that fxy is a nice function. In fact, for this, all we need is a continuous function that or not even continuous, a function that has partial derivatives, but let's assume that everything is C1, so continuous partial derivatives, everything is differentiable. Then the gradient of f at the point x0, y0 is 0. What's written here is phrased slightly differently than the way we wrote it last time. Last time we wrote, but tell me if you agree that it's precisely the same thing, that the derivative of f with respect to x at x0, y0 is 0, as is the derivative of f with respect to y at x0, y0. Do you agree that writing this and writing this is precisely the same thing? Everybody? Good. Okay, so looking at a function, seeking out points where the gradient is 0, gives us points which have the potential of being minimum or maximum. We call those critical points. Now we want to classify them. We want to find a way of saying, hey, this is indeed a minimum. Hey, this is indeed a maximum. Hey, this is a fraud. He's not really one of those. He's either a saddle point or some form of false alarm. Okay, and the way to do that is going to be a theorem, which resembles what we call the second derivative test in Calc 1. Okay, so what we're going to be looking at is the second partial derivatives, and some criteria on those is going to help us classify these points. I'm not going to write the theorem. I'm going to build up to the theorem. We're going to see how we get to the theorem. So instead of writing the theorem and then writing proof, I'm going to write the proof first. We're going to find the theorem. Let's see how we do it. So I want to remind you of Taylor's polynomial. We're going to use the Taylor polynomial. Don't freak out, only to degree 2. Okay, so that's not too bad. So fxy, it's Taylor polynomial. I'm going to write the polynomial, and then there's going to be a remainder term. Okay, so what is it? It's f at 0, 0. Instead of working around the general x0, y0, I'm going to work around the origin, 0, 0. Okay, so let's start here. Let's add, assume that 0, 0 was found to be one of those critical points, one of those candidates for being a minimum or maximum. Satisfies fx at 0, 0 equals fy at 0, 0 equals 0. So it's a candidate for being a minimum or a maximum. Okay? So now I'm going to write the Taylor polynomial. So it's f at xy equals f at 0, 0 plus, what's the term that's going to appear next? It's going to be some expression involving the first partial derivatives, right? But I'm assuming that those are 0. Do you agree? So if 0, 0 satisfies this, then the term involving the first partial derivatives vanishes. Do you agree? Okay. Plus, now there's going to be the term involving the second partial derivatives, and I don't know that those are 0. Okay, so there's going to be the term, let me remind you what it is. It's 1/2. The 1/2 comes from 1 over 2 factorial, remember? And then what we're going to have here is x squared times fxx at 0, 0, plus 2xy fxy at 0, 0, plus y squared fyy at 0, 0. Does this look familiar? Do you remember we did this? Everybody? Wonderful. Now these two things are not equal because there are all the other terms, or if we just write the polynomial, plus, let's call it remainder. Okay? There are formulas for the remainder, but I don't need them now. Okay? I'm just going to write there's some remainder term. Remember that the remainder is of magnitude, it reflects terms that have powers higher than 2 in them, right? So if I were to continue, I would have, the next term would have x cubed or expressions involving both x and y, but where the total, the sum of the powers is 3, okay? So the next expression is a polynomial of degree 3 and so on. Do you agree? Okay, good. So let me rewrite this. I'm rewriting this. I'm writing fxy minus f00 equals this expression, but now I'm going to use some names. So I'm going to write 1/2 x squared. I'm going to call, just to make our discussion less blurry, I'm going to call temporary names. I'm going to call this a, the derivative, the second derivative twice with respect to x at the point 0, 0. I'm going to call the mixed partial b, and I'm going to call this one c. These are just temporary names. Okay? So what I get here is 1/2. Let's write it like this. 1/2 ax squared plus 2bxy plus cy squared do you agree? Plus this remainder. But recall that the remainder only has terms which are with powers that are 3 or higher. And I claim that the things in the remainder in this case are negligible. Why are they negligible? So think that I'm looking at x's which are close to 0, 0. Oh, sorry, x's and y's which are close to 0, 0. Being close to 0, 0 means that both x and y are small. When I raise them to powers, what happens to numbers that are smaller than 1 when I take powers of them? They become even smaller. So when I take something, let's say 1 over 100, if I square it, I get 1 over 10,000. Do you agree? If I take it to the power 3, it's already 1 over 1,000,000. Do you see that? Okay. So the stuff that lives here, and I'm being not completely formal, but this is the idea. Everything can be formalized using epsilonautics to be a rigorous proof, but this is the idea, and the idea is what's important right now, that the stuff in the remainder is negligible. When I'm looking at points near 0, 0, when I'm looking locally, I'm just checking to see if 0, 0 is a local minimum or a local maximum. I want to know if for points around 0, 0, the values of the function are always smaller or always bigger. Is that clear? So I'm going to write here plus, I don't have room for the word negligible, plus, let's write it down here, plus negligible. How do I spell that? I? I? A? Like this? Does that look right? How do I spell stuff like this? Do you agree? Good? Okay. Now, we're going to see that this negligible stuff still plays a role. Okay, don't just throw it away and forget it. It's going to have a certain comeback a bit later. Okay. So, what's the bottom line of everything I wrote so far? I want to know, when can I guarantee that the left-hand side is always positive? If it's always positive, if this is always positive, it means that fxy is greater than f00 for every x and y. Do you agree? Okay. If this is always positive, then f00 is a local minimum. Does everybody see that? Yes.
Could be also always negative?
Yes. If the left-hand side is always positive, that means that fxy is greater than f00, which means that f00 is a local minimum. If it's always negative, by always I mean for every xy near 0, 0. If it's always negative, then f00 is a local maximum, because the value of fxy is smaller at every nearby xy. Do you agree? And if for some xy it's positive, whereas for other xy it's negative, then this point is not an extremal point. Do you agree? So let's write that. So if left-hand side is positive for every xy near 0, 0, then 0, 0 is a local minimum. Do you agree? Everybody? And let's use a different color. If the left-hand side is negative for every xy near 0, 0, then 0, 0 is a local maximum. Do you agree? One sec. And if for some xy it's positive and for some xy it's negative, then 0, 0 is neither. Okay? Yes, question?
Why are you specifying left-hand side?
The left-hand side of this equation that I wrote.
So,
This is what I call left-hand side.
so what's the right?
This?
If they're equal, wouldn't they have the same side?
Yeah, that's the next thing I'm going to say.
Okay.
Okay? So if this is positive, then it's a local minimum. So what I have to check is this positive? Because they're equal, exactly. Good? Okay. So does everybody agree to this analysis that we're... Stop me whenever something is not clear. So what I have to check, do you agree that the 1/2 does not have any impact on whether it's positive or negative? So what I have to check, is this expression positive or negative? Okay. So we need to decide about positivity or negativity or neither of the expression ax squared plus 2bxy plus cy squared. Does everybody agree? Okay. Now how do we do this? So we're going to run through a certain kind of a bit tedious, not that bad, analysis of this expression and see what can we say regarding a, b, and c, and how do these coefficients, remember what a, b, and c are. They're the partial derivatives of f at the point 0, 0, the second order partial derivatives of f at the point 0, 0. Okay? And we're going to see that some relations between them determine whether this thing is positive or negative or neither. Okay? So let's do that. So assume we're going to have several cases. Okay, let's assume first that a is not 0. This is going to be, bless you, the first case that we're going to study. A is not 0. I'm going to rewrite this as ax squared plus 2bxy plus cy squared. I'm going to rewrite it. It's going to look like I'm taking something nice and compact, bless you again, nice and compact, and making it a bit uglier, but there's a reason. That's what's going to enable me that's going to reveal the conditions that determine whether it's positive or negative. So I'm first going to rewrite it as a times x plus b over a y, all of this squared, plus y squared times c over a minus b squared over a squared. This is just an algebraic identity. Tell me if you agree. Let's do it together. So here we have x squared times a. That's this ax squared. Do you agree? Plus 2 times xy b over a. 2 times xy b over a multiplied by a. So it's 2 times xyb. That's this thing. Plus b squared over a squared times y squared, which cancels out with this b squared over a squared times y squared, because it has a minus in it. And the last thing that we have is y squared times c over a times a, which is cy squared. So does everybody agree that this is true? Okay. And I'm going to take one more step and rewrite that as a times x plus b over a y, all of that squared, plus y squared, and I'm going to do a common denominator here. So I'm going to get ac minus b squared divided by a squared. Do you agree to this? Good, everybody? Okay. Now let's draw conclusions from this. I'm going to write and then explain. Okay? So, if AC minus B squared is positive and A itself is positive, then let's see what happens. If AC minus B squared is positive, this is positive, I'm dividing it by something squared, this is positive. I'm multiplying by something squared, the entire thing is positive, or at least non-negative. Okay? Do you agree that this entire term is non-negative? So is this, because this is always squared. So for every, and I'm multiplying the entire thing times A, but A is also positive. So if these two things hold, then the entire expression is non-negative. Do you agree? And this means that the left-hand side is non-negative, and we already agreed that that means that 0, 0 is a local minimum. Do you agree? Then 0, 0 is a local minimum. Did everybody follow that? Good? Yes?
Is it enough to say that AC minus B squared is bigger than or equal to naught? To 0?
You're asking if this could be 0 as well. I guess it could. Eventually, we're going to have this break into various cases in total, and in fact, I'm not sure. What happens if it's 0? No. The answer is no. We'll see it in a minute. Okay? If it's 0, then this term is guaranteed to vanish for any y, and then different things are going to happen. Wait. Good question. Okay. Does everybody agree to this? Okay. If AC minus B squared is positive, but A is negative, then by the exact same argument, this entire thing inside the brackets is non-negative, but I'm multiplying it by something negative, it's non-positive. In which case, 0, 0 is a local maximum. Do you agree? Everybody? Good. If AC minus, I think we're going to need another board. So, but I want to keep this on it. I'm going to rewrite things. Did everybody finish copying up to these ifs? Okay, and if you're at home, you can press pause anyway. So let me rewrite this. ax squared plus 2bxy plus cy squared. And I'm going to erase this, and then I'm going to continue up on the top. Remember, we're assuming that a is not 0. This is the case we're handling right now. If a is 0, we're going to have to handle this completely differently because this is illegitimate. We can't write it this way at all. Do you agree? Because we're dividing by a's here. Good? So the case a equals 0 is going to have to be handled separately. Okay, but the case a equals 0, by the way, is easier because I can just plug in a 0 here and I'm left with this. Do you agree? Okay, back to where we were. So we handle these two if ac minus b squared is negative. The claim is that if it's negative, then the point 0, 0 is not an extremal point. It's not a minimum or a maximum. It's some form of saddle-ish point. In nearby points, you have lesser values, and in other nearby points, you have greater values. Then, 0, 0 is not a local extrema. Why? Why is that true? Because if y equals 0, if I look at points where y equals 0, what do I get? I get, when y is 0, this entire thing vanishes. It's 0. Do you agree? And this thing is non-negative, because I'm squaring it, and I'm multiplying it by a. Do you agree? So the entire thing depends on the sign of a. If a is positive, the entire expression is positive. If a is negative, the entire expression is negative. Do you agree? Does everybody see that? If y equals 0, for any point where its y is 0, then let's call this entire thing star. Star is positive or negative. Let's write. Then star has the same sign as a. Do you agree? Yep. Okay. Now look on points. Let's replace this if by writing this. For points x, y, such that y is 0. For points of that form. The expression has the same sign as a. So if a is positive, the value of the function at these points is positive. If a is negative, it's negative. Okay. For points x, y, such that x plus b over a y equals 0, these are legitimate points, right? You can write that x equals minus b over a y, right? So for these specific points, what do we have? This thing is 0 now. So this entire thing is 0. What about this thing? AC minus b squared is negative. I'm multiplying it by things that are non-negative. So the entire thing is negative, right? And it has, and then I'm multiplying it by A. So it has the opposite sign of A. If A is positive, it's going to be negative. If A is negative, it's going to be positive. So star has the opposite sign of A. So if A was positive, I can find points such that star is positive and such that star is negative. Likewise, if A is negative, I can find points such that star is positive and star is negative. Do you agree? So in this situation, I can find points at some of which it's negative, at some of which it's positive. It's not a maximum. For it to be a maximum, it has to be always negative. For it to be a minimum, it has to be always positive. Clear? Okay. So this is not a local extrema. Let's proceed. So we handled the situation where AC minus B squared is negative. We handled the situation where AC minus B squared is positive. We split it up in two cases depending on A. So the remaining situation to look into is what you mentioned earlier. What if AC minus B squared is 0? Okay, one sec. If AC minus B squared is 0, then all of this vanishes for any x and y. So we're left with just this. Do you agree? Okay. Now, we're left with just this, but then for points for x, y, such that x plus b over a y equals 0, points like this, this is 0 because we're assuming that we're in the case where AC minus b squared is 0. Look at those points that satisfy this, as near as you want to 0, 0. Do you agree that this is going to be 0 as well? So the entire expression is 0 at these points. Do you agree? Tricky. Does that mean anything about fxy minus f0, 0? Let's look one board back. We found that this entire thing is 0 at these specific points at that situation. Meaning this entire thing is 0 at these specific points in this situation. Looking one board back, this is 0. Do you agree? But if this is 0, the negligible stuff is no longer negligible. If this thing vanishes, then the negligible stuff becomes the essential stuff. That's where the information lies. Do you see that? So in that situation, we can't say either it's a minimum, or it's a maximum, or it's not extremal. We can only say, oops, give up. We have to look at higher order derivatives. That phenomena occurred in the second derivative test in Calc 1 as well. If the second derivative was positive, it was a minimum. If the second derivative was negative, it was a maximum. If the second derivative was 0, we don't know. We have to look at higher order derivatives in functions of one variable. Remember that? Okay, so same here. So if AC minus b squared is 0, then for x, y satisfying this, we get star equals 0. The entire expression vanishes. In which case, all this discussion cannot decide for us whether it's a minimum or maximum. In which case, we don't know. Because the higher order derivatives now play an essential role. They're no longer negligible. Is this clear so far? Okay. So we still have to take care. So everything we did was we covered up all the different situations for A which is non-zero. Okay. When A is 0, this expression becomes more user-friendly, and I'm going to leave it to you to use exactly the same arguments, but simpler, because there's no A, to decide how you classify according to B and C. Okay? So, when A equals 0, ... homework. And the bottom line is the following theorem. Now I'm going to write the theorem. Theorem. Did everybody write when A equals 0, ... I want to erase it and write the theorem on top so we can keep it on the board for the example we're going to do. So the theorem, so this is the second derivative test, or the two-variable version of the second derivative test. So here are our assumptions. We're assuming that fxy is not only C1, but C2, that it has second-order partial derivatives, and that they're continuous, so the mixed partials agree, okay, is C2 at least. Usually we're going to assume higher or whatever, near x0, y0. Now I'm going to replace all the 0, 0s with x0, y0, okay? And the analysis that we performed is precisely the same. Just everywhere that we had x, we're going to have x minus x0. And everywhere we had y, it's going to be y minus y0. Okay, but it's the exact same idea. So that's one assumption. And the other assumption is that we're looking at a critical point. And fx at x0, y0 equals 0 and equals fy at x0, y0. Okay, this means that we're looking at a critical point. Okay, a Fermat point. Denote A equals fxx at the point, B equals fxy at the point, and C equals fyy at the point. These are the A, the B, and the C that we've been using. Then, and the case where A equals 0 turns out not to add new information. So the various cases that could happen there actually fall into the cases which we already handled for A non-zero. So the bottom line of the theorem is, if AC minus B squared is positive, then x0, y0 is a local extrema. And if A is positive, then it's a minimum. And if A is negative, it's a maximum. And if A is 0, it's not. Okay, if A is 0, it's going to fall into the other cases. If AC minus B squared is negative, then this is the situation in which we had no local extrema. Then x0, y0 is not a local extrema. And if AC minus B squared is 0, then we don't know. We don't know, meaning the theorem does not provide us with information. We have to look into further theorems, which we're not going to mention in this course. I doubt you mentioned them in Calc 1. Theorems that classify, there is things that do that. Classifying local extrema according to higher order derivatives. Okay, in Calc 1, the theorem is for general n, and it depends with whether n is even or odd, and I don't know if you've seen that theorem, but there is such a theorem. Okay? And it turns out that when a equals 0, in the case a equals 0, only these two things happen. So there's no a equals 0 in this situation. It can't happen. Okay? When you do the analysis for a equals 0, you'll see that only these two things can happen. Okay, so is the theorem clear? Okay, so the second derivative test, the so-called second derivative test for functions of two variables, in fact, don't look at only the signs of a, b, and c, but look at a certain relation between them. Okay, this ac minus b squared. Clear? Let's do an example. Question, yes?
When you say that ac minus b squared is less than 0, or is negative, why don't we say that it's not an extrema at all?
What do you mean is not an extrema at all?
Like, why do we say it's not a local extrema?
Because this is what we're studying, whether it's a local extrema or not. Of course, if it's not a local extrema, it can't be a global extrema, right? But a point can be a local extrema without being a global extrema. So this result is even stronger. It's saying even locally, it's not extremal. It's some form of saddle-ish behavior. At nearby points, you can have greater values and lesser values, so the point itself is not, even locally, it's not extremal. Okay? Here we're getting that it is local, minimum or maximum. Okay? That still doesn't tell us about the global behavior. For the global behavior, we're going to have to do something more. Either if we found 6 of them and that's it, then compare all 6, or there are going to be more different phenomena, like checking endpoints. And endpoints, I'm doing this because endpoints for two variable functions, it's not just the two endpoints of the interval, it's the entire boundary. Ooh. That's quite a few of them, not just 2. That's infinitely many of them. So there's going to be a further theory, and there is. Okay? Okay. Good. So let's do an example. The example that I want to do, in fact, is to continue an example that we started with for Fermat, for classifying so here's Fermat's theorem. Before I erase it, we did an example when we discussed this theorem. We found the critical points. I'm going to write the example in a minute. So now I'm going to classify those points that we found in that example. So I'm going to remind you what the example was and what we found, and then we're going to classify them using the second derivative test. So example. The function that we were looking at was the function x squared y plus xy squared minus xy. Remember this example? And we found that fx was 2xy plus y squared minus y, and fy was x squared plus 2xy minus x. And we found that critical points, maybe let's make a, I'm going to write it on a separate board, the critical points, because we're going to need some. I'm thinking maybe I can fit it all in one board. That would make life easier. Let's try fitting everything in one board. So the critical points that we found, the points where both fx and y are 0, I'm not going to solve it again. We took a y common factor out of this one and an x out of this one. Remember what we did? So the points that we found were 0, 0. That was one of them. 0, 1. 1, 0. And the last one was 1/3, 1/3. Those were the points that satisfy both fx and fy equal 0. Okay, so these are the critical points. Okay, so this is what we found. Now I want to decide if they're minimum or maximum or neither. So what do I need? I need the a, the b, and the c, which are the second order partial derivatives. So a, which was fxx, is the derivative of fx with respect to x. So what is it? It's 2y. Do you agree? B, which was fxy, is the derivative of fx with respect to y, which is 2x plus 2y minus 1. Do you agree? For the same price, you could take the derivative of fy with respect to x, because they're equal. The derivative of fy with respect to x is 2x plus 2y minus 1. Same thing. Whew. Right? Okay. And c was fyy, which is what? The 2x. Does everybody agree? Now we have to calculate these separately at each of these points and determine whether a is positive and whether ac minus b squared is positive or negative or 0. Okay, so let's do that. So at the point 0, 0, a is 0, a equals 0 because it's 2y. B is 2x plus 2y, which is 0 minus 1. So b is negative 1. And c is 2x is 0.
Once we know that a is 0, can't you just stop?
No, because it also depends on what ac minus b squared is.
But didn't you say earlier that if a is 0, it'll always be...
Either negative or 0.
Right.
So I still have to determine if it's negative or 0. Okay? So a is 0. What is ac minus b squared? ac minus b squared, this is hard. This is 0 minus, in fact, I don't care what b is as long as it's not 0 itself. So this is going to be negative. ac minus b squared is negative 1 squared is 1, so it's negative 1, which is negative. Do you agree? Okay. So what's the conclusion regarding the point 0, 0? Imposter. Not a real extremal point. Okay? No extrema. Or not extrema. Do you agree? Yes.
Do we have like a special criteria for when a is equal to 0?
That's what I said. I left that to you to calculate as homework. I had a equals 0, ... do the calculations. And it turns out that it breaks into cases, but it only falls into the cases where ac minus b squared is negative or ac minus b squared is 0. That's the only two things that could happen. And it falls into precisely the same cases that we had when a is not 0. So we can just, when we write the theorem, everything combines into just those cases. You don't have to separate a equals 0 as a separate case. Okay, but you have to do the calculations, the analysis, in order to see that that's in fact the case. Okay, what about 0, 1? At 0, 1, x is 0, y is 1. So a is 2. B is x is 0, y is 1. So 2 minus 1. B is 1. And C is 2 times 0, C is 0. Good? Good. A is positive. Note that A is positive. What is AC minus B squared in this case? C is 0, so AC is going to be 0. And B is 1, so it's again negative 1, and it's again negative. So again, we're in the situation where this point is not an extremum either. Do you agree? What about 1, 0? So I'm just plugging in the values. So A is 0, B is 1, C is 2, and AC minus B squared is again negative 1, is again 0, and this point is not an extremum either. We have one last hope. 1/3, 1/3. So what is A? A is 2/3. B is 2/3 plus 2/3. That's 4/3 minus 3/3. B is 1/3. And C is 2/3 as well. Good? And AC minus B squared is what? A times C is 4/9 minus 1/9. So it's 3/9, so it's 1/3, so it's positive. Yay! Okay, so AC minus B squared is positive. A is positive, so what is 1/3, 1/3? Minimum. Yes?
Do you always have only one different extreme?
No. We're going to do various examples, and this is very specific what happened here. You can have many extremal points, local extremal points. You can have none. Anything could happen. Anything could happen. Okay? We've seen examples that have none. Remember x to the 4th minus y to the 4th? You could do the same analysis for that function, calculate the second derivatives, and we argued for logical, more basic reasons that it has no extremal points. Okay? Okay, questions, further questions about this. So the last thing I want to say is something a bit more general, just notation. So remember what we were looking at. If you can look a second at this board, the expression that classified was this expression, ax squared plus 2bxy plus cy squared. This is what we were using, remember? And we found out that from this thing, all the information is somehow hidden in the sign of A and the sign of AC minus B squared. Remember that? Okay, that's what we found out. That's what the theorem says. Okay, look at the theorem. It breaks according to the sign of AC minus B squared. And in this case, it breaks into two subcases, whether A is positive or negative. Do you agree? So it turns out that this theorem is a special case of a more general thing that holds for functions of many variables, not just f of x, y. And that this thing here turns out to be a certain 2 by 2 determinant, which in general is an n by n determinant. And it has a name. It's called the Hessian. So I want to write all that very briefly. So note that this expression, ax squared plus 2bxy plus cy squared, I can write it a bit differently in terms of matrices and vectors in the following way. It's xy times the symmetric matrix A, B, B, C times xy. This and this are the same thing. You all know matrix multiplication, right? So if you multiply this, you get ax plus by in the first coordinate and bx plus cy in the second coordinate. And then you multiply by this. So you get x times ax plus by plus y times bx plus cy. And if you sum everything, that's what you get. Okay? And this matrix, what determined the positivity of this expression, which is called the quadratic form, that's what it's called, was two things. Was whether A was positive and whether the determinant of this matrix was positive. Or let's write it differently. The signs of this determinant, this is just saying AC minus B squared. Do you agree? That's precisely what we were looking at. And A itself determined the positivity of the expression, the quadratic form. This thing. Star, what we called star previously. Do you agree? Okay. So this thing, recall that A, B, and C are not just numbers. They were, we didn't know. This thing was fxx, fxy, fxy again, and fyy. Right? This is this matrix. Do you agree? And this matrix has a name. It's called the Hessian Matrix, corresponding to the function f, okay, of fxy. Okay, and in this course, I'm not gonna go into higher order or more variable examples of this, but in general, one can write the Hessian matrix for a function of three variables. It's going to be fxx, fxy, fxz. Always the second order partial derivatives. And it's always going to be a symmetric matrix. And what's going to determine the positivity is going to be so suppose this is a 3 by 3 matrix with three variables. So it's going to have all the six different partial derivatives, right? Because it's symmetric, fxy and fyx are the same. So what's going to determine its positivity, and that's a theorem, it's called Sylvester's theorem, and we're not going to get into it, is the sign of A, which is just this determinant, right? This is A. The sign of the determinant, the 2 by 2 determinant. And if it's a 3 by 3 matrix, you have to look at the 3 by 3 determinant as well. Okay? Clear? So that's in general, so I'm just going to write this can be generalized to fxyz, etc. Okay, we're not going to go into further details. I just want you to know that such a thing exists. It's usually denoted h of f, the Hessian of f, etc. Okay. Questions? Yes?
Like, what do you mean that the signs of the matrix and A determinate the positivity of the derivative?
That's what we saw. the positivity of this thing was determined by the sign of A, whether A is positive or negative, and the sign of this determinant, which is AC minus B squared. That's how we do a 2 by 2 determinant, right? We discussed that. Clear? Good, everybody? Okay. So this wraps up this discussion, the second derivative test. It's two-variable version. What we want to do next is what you hinted at before. We want to look at situations where we're not only considering critical points inside a certain domain, but we also have to take into account what happens on the boundary. Okay, just like in single variable, critical points were not just points where Fermat points, where the derivative is 0. Critical points were also points where the endpoints, for example. Okay, we have to look at endpoints. And endpoints, where in 2 dimensions, it's not just the left end and the right end, it's the entire boundary. There are infinitely many points on the boundary. What do we do? Coming up next.